Hello, my name is Marco Lisi. I work for the European Space Agency. Let me go back briefly to Shannon's theorem and Shannon's equation. And let me make some consideration about the physical meaning of this formula. We said that one important message is the quality of communication transmission depends from a ratio signal over noise. We will see in a minute that noise is related to temperature. But what is noise, in fact? Noise is a chaos, is a disorder. What is the information? Information is something ordered. So here the conclusion of that we derive from Shannon's theorem, which is not a surprise, because this is not just a law, a mathematical law that has to do with the transmission, with information theory. You see, through the Shannon's equation, in my view, we have a link between the information and mathematical domain and the physical domain. So we discover that there is a coincidence of results as deriving from the laws of physics, and particularly from the laws of thermodynamics. What does the second principle of thermodynamics and also the third principle give us? They tell us that the entropy of the universe can only increase. What is the entropy? Entropy is, in fact, is a measure of disorder. Is the fact that the energy degrades and is transformed more and more continuously in heat, and which is represented through a temperature, and this is a sort of irreversible type of mechanism. So there is no way, once I have disordered something, to re-establish the order without a loss. And the loss is an amount of the entropy of the disorder somewhere else. So I cannot restore a situation effectively, having 100% efficiency in the process. This is not possible. This is what the second law of thermodynamics, the third principle of thermodynamics, tells us that the entropy is of the universe, since the universe is considered, as it probably is, a closed system, can only increase. So, if you want, in our universe, we have a continuous fight between order, if you want, information, and chaos, that is noise. Noise, chaos, lack of information. Now, let's go back to the schematic of a satellite link that is shown in this slide that we have already seen before. We said that we are limiting ourselves to one side of this full satellite communication link, that is the downlink, the so-called downlink. It's just a way to simplify things. I could have considered the uplink. They are mirror image one of the other. So the same consideration would apply in one case or the other, just reversing the role. In one case is the satellite receiving, in the other case is the satellite transmitting. So it's just a simplification to limit the lecture to a simpler somehow case. So let's consider the link between a satellite and ground station. We started saying on board the satellite we'll have a transmitter with a power amplifier delivering a certain power to an antenna on board the satellite. Then the signal transmitted by the satellite antenna will experience a certain losses. First of all, it will travel through a certain distance from satellite to Earth. It will experience a certain losses due to the geometrical characteristics of the link, the fact that the energy is spread, the power is spread over the famous sphere, free space path loss, then other losses, for instance, the atmospheric losses, rain, and so on. Then we get to the antenna, we said, the antenna of the ground station, and the power derived from the antenna is fed into the receiving chain. But so far, we have only dealt with the signal. In fact, the outcome, important but not sufficient, of the Friese formula was a P sub r. P being the power of the signal received. And what about noise? We know now from Shannon's theorem and Shannon's equation that we have to consider noise, because eventually, at the end of my receiving chain in the ground station, the quality of the information that I reconstruct, demodulating, decoding, and whatever you might think from my received signal, depends not only on the level of the signal. So the fact that the P sub r, the level of the received signal at the input of my receiving chain in the ground station, is high or low per se doesn't mean anything. I want to compare it with the noise. Noise where? Noise at the input of the receiving chain, so at the same interface. Now, the noise, in fact, comes also from the transmitting end. Here I am simplifying. I consider that on the transmitting end, so from satellite, the signal over noise ratio is ideal, so infinite or very high, so high that I can neglect it, which is not always the case. This will not be covered in this lecture, but eventually I can say that the total signal over noise ratio in a complete link, up and down, comes from the contribution of both uplink and downlink. In this case, just to simplify, I have considered the S over N from on the transmitter end, let's say from satellite, as being a sort of ideal, so good that you can neglect it. So at this point, instead, I want to know about the noise that is introduced at the receiving end in the ground station. And then I have to see if there is any noise deriving from the antenna, and I will have the surprise to know that even the antenna introduces noise, and we'll see why. And then to consider the noise that is introduced before the modulation by the receiving chain itself. And I have somehow to define this ratio S over N. Actually, we'll see that is not defined in terms of S, but this is something I anticipated. I'm using a different symbol for the signal over noise ratio, but this ratio anyway will tell me how good, in fact, is the communication link and what I can expect after demodulation in terms, for instance, of errors out of the demodulation. So I have to understand, and we get back also to the consideration about the laws of thermodynamics, the concept of thermal noise. One unavoidable source of noise everywhere. Everything in our world generates noise, and it is coming from the thermal agitation, in fact, from the temperature of everything around us, including ourselves. We ourselves are a source of noise. We ourselves are an antenna radiating, and being at a certain temperature, we are producing noise. So let's consider a component. It could be a resistor, for instance. It's a passive component, so something that we would say, okay, passive component like a resistor, it cannot generate anything. It's a passive, it's not amplifying, it's not dealing, which is not true. Okay, let's suppose in this slide I have shown a box that could be, for instance, a resistor, and then what I can actually measure is not just theory, but I can measure it, that the thermal agitation created by the temperature of the resistor, because this resistor, this component is at a certain temperature. There is only one case when there is no thermal agitation, so when the temperature is 0 degrees Kelvin, the absolute zero. Unfortunately, this temperature cannot be achieved. And again, this because we cannot go against the laws of physics. So we can get very close to the 0 degrees Kelvin, but we can never achieve it. Because if we could achieve it, then we would get an ideal situation where there is a perfect order. And the perfect order and no chaos, no entropy is not achievable. Okay, so this agitation of the electrons, for instance, in a resistor, statistically creates a difference of potential, so a voltage across the resistor itself. And in fact, I can measure this voltage, and I can even derive power from this voltage. It's very, very tiny level of voltage and very, very tiny power, but it is physically existing. And the formula giving me the power in watts of the noise generated by the temperature is called thermal noise or Johnson noise, is P sub n, noise power in watts, that is deriving from the multiplication of three factors. One is the bandwidth, which tells me that in fact the noise has a sort of an infinite bandwidth. So the more bandwidth I consider for my measurement, and the more power I get. So one could say then if it is infinite bandwidth, I could get infinite power. Well, in practice, this is not the case, because there will be other factors limiting. It's not an ideal resistor. I have to match over an infinite bandwidth. In fact, this is not achievable. But let's say, given the bandwidth, the larger the bandwidth, the more noise I collect from, for instance, this component, passive components. It could be a resistor. Then at the temperature, we said, of course, that is thermal noise, so it depends on temperature. The higher the temperature, the higher the noise power, and being expressed in Kelvin, though. Okay, so P sub n would become 0 only when T in Kelvin is 0, so 0 degrees Kelvin, while usually we consider as a reference temperature, or so-called the room temperature, the temperature of 290 degrees Kelvin that corresponds approximately to 17 degrees C. This is usually defined as a reference or room temperature. And then there is a constant, very important constant, that we'll see in our final link equation. So it's important to remember it, especially in its dB form. The Boltzmann constant, that is equal to 1.379, so 1.4, by 10 to minus 23, so it's a very, very small value, and it expresses the dimensions of Boltzmann constants are Joule over Kelvin. In other words, Joule is a measure of energy, is watts over Hertz over Kelvin. Hertz is second to minus 1, so Hertz at denominator means seconds at numerator, seconds by watts is energy, power by time is energy, so Joule over Kelvin. So these are the dimensions of the Boltzmann constant. So this is a way really to measure, it's the law of physics. I can measure the noise power, and it is equal to this formula here. Boltzmann constant by T in degrees Kelvin by the bandwidth of measurement, let's say, I consider in my measurement.